Now we want to really start focusing on these conditional statements. Because like I said, this is what most theorems in mathematics will consist of, is a conditional statement. It'll say if something, then something, right? So if P, then Q. So you have some list of conditions, and then you show that, if those are true, then they satisfy this conclusion, essentially. Okay. So let's just start with just a basic example here. I'll put the examples in a different color here. So if x equals 3, then x squared equals 9, right? So just something simple like that. And we might just write this as x equals 3 implies x squared equals 9, right? That's probably how I would type it, for example. So let's look at different versions of this statement. Okay. So we typically can look at 4 different versions of a statement. So this is what we would call the positive. Okay. If P, then Q, the original here, right? i.e. P implies Q. Then there's a few different ways we can rearrange it. One, we can look at the converse. This would be if Q, then P. Okay, Q implies P. So these are not always both true, right? Just because P implies Q does not mean that Q implies P. For example, x squared equals 9 does not imply x equals 3, because x equals 3 or x equals negative 3, right? So it's not necessarily true that x squared equals 9 implies x equals 3, because x could be negative 3, right? So the positive and converse are not what we would call logically equivalent. Okay, so two statements are logically equivalent if, the technical definition is if they have the same truth value for all possible combinations of truth values for all of the variables in the expressions. Okay, so let me just write up here, logically equivalent. Okay, we write this as P, and it's like an equal sign but with 3 lines. Okay, here we would say, we read this as P is equivalent to Q. Sometimes you see this in math, like with just numbers. It's not common, but I mean, it's just another way to write equivalent. So sometimes you might see it instead of an equal sign or whatever. You might see it for like functions, for example, if they're completely equivalent, because like we might use f of x equals g of x a little loosely. For example, if they're the same but not on the entire domain. It's just a bit of a tangent, but just to give an example of what I mean, like if we might say that x plus 3 is equal to x plus 3 times x minus 3 over x minus 3, right? Because these cancel, but we wouldn't say that they're equivalent because they're not. So if they're actually equivalent, then you might see a stronger statement like this one. But again, I don't think it's super common, just thinking of things, times I've seen it before. So the converse is important because I think often our first instinct is, if we get a positive statement and we prove it's true, then we want to say, okay, well, what about the converse? Is the converse also true? And you might immediately be able to dismiss it as, no, of course it's not true. But if it is, then, that's something we want to know, because if the positive and the converse are true, then that means that P and Q are exactly the same. I'm sorry, I shouldn't have written P and Q here, because that's not exactly what I mean here. Because P and Q we're using as the component statements, but I'm talking about like the big overall statements, which we called S earlier. So let's say like S, S1 and S2, for example. So if the individual component statements, if the positive and the converse are both true, then the individual component statements, that means, are equivalent. equivalent in like a different sense, in that P implies Q and Q implies P, so they imply each other, meaning that if you have one, then you have the other. So, an easy example of that is if you have like x plus 3, x equals 3, implies that x plus 2 is equal to 5, right? But this is also true in the other direction. So in other words, these are saying the same thing, right? Which is what allows us to solve equations like the right-hand one. Okay. So anyway, so let's go on to, okay, what if we start throwing some negations in there? So we might have the inverse statement. So the inverse statement is the original negated. So if not P, then not Q. Okay. So this is actually logically equivalent to the converse. Okay, you could see it by writing out the truth table. So you could see, okay, if you write out the implication statement and you look at, okay, the truths and all that, you see that they have the same values. So, and it'll be a little more obvious when we look at actual statements like up above. But let me write out this last one first, because this one's also really important. The contrapositive. Okay, so this one is a complete negation of the original statement, including flipping the order. So this is if not Q, then not P. Okay. So logically speaking, the positive statement is equivalent to the contrapositive. Okay, and this is really helpful because, again, it gives us another avenue of proving things. Because maybe the positive statement is hard to prove, but the contrapositive statement is easier to prove. And then you might notice that the inverse is actually just the contrapositive of the converse. So that's why those two are logically equivalent as well. Okay. So let's look at an example. So, the positive statement maybe would be if x equals 3, then x squared equals 9. Okay. Well, then the contrapositive of this would be if x squared does not equal 9. Well, in that case, then certainly x cannot be 3, right? So we can hopefully see why these would be the same, right? If the first one is true, then the second one is also true, and vice versa. If x squared is not 9, then x cannot be 3, right? Because if x was 3, then x squared would be 9, right? So they're just kind of saying the same thing. Okay. The converse here would be, so let's say this is true. This is true. If x squared equals 9, then x equals 3. Okay, that's not true, as we already saw. And the inverse tells us the same thing, so we should expect the inverse to not be true, which is that if x does not equal 3, then x squared does not equal 9. Well, that's not true, because x could be negative 3, and then x squared would be 9, right? So we know that's not true. So these two go together, and these two go together. If one of them is true, the other one's going to be true, and vice versa. So again, this is helpful because it gives us a nice avenue of how to prove things. So like maybe we prove the contrapositive instead of the positive. So now if positive and converse are true, then we write P if and only if Q. Okay, so this is very important because if you're asked to prove, or if an author proves a statement that looks like this, you have to show it's true in both directions. So P if and only if Q is saying that P implies Q and Q implies P. So there's two different things you have to prove there. And we often combine these into P, and this is read as if and only if Q. Okay, so they imply each other. Okay, so very important here. I remember when I first started doing proofs, somehow I missed this completely. And I would get if and only if proofs, and I would only prove one way, and I would miss half points every single time. So very important to prove both directions here. So building on our example here, we could say, for example, x squared is equal to 9 if and only if, which by the way we abbreviate as IFF, if and only if x equals 3 or x equals negative 3. Right, so we could make a statement out of that. So x squared equals 9 implies x equals 3 or x equals negative 3. And x equals 3 or x equals negative 3 implies x squared is equal to 9. Right? So we use this stuff all the time in math, just without really thinking of it in this context. But now that we're getting into proofs, it's better to frame it this way. So now last thing I want to look at with these statements is what we call De Morgan's laws. Okay. These are common in sets. Like, I would think that, I don't know exactly what the order of the content is and exactly what's included, but I would think in probability theory, this would be one of the first things you go over. So we're going to look at it with statements, but you can apply the same logic to sets. So I'll write them both out here. So there's two De Morgan's laws, basically, which the first one says that the negation of P and Q is equivalent to the negation of P or the negation of Q. Okay. So it's kind of like you're distributing that negation, and when you do that, the and turns into an or. Okay. So for sets, the way we would write this is that A and B complement, because this is how we write negations for sets, is equal to A complement or B complement. Okay, and we'll look at that when we look at sets a little bit more in depth. We can show that those are true. And then the second one is that not P or Q is equivalent to not P and not Q. Okay. Again, this would be A union B complement is equivalent to A complement and B complement. Okay. So I think maybe we could see this just, I think here you would just do the truth tables to show it. Here with sets, I think it's easier to draw pictures and look at, exactly what's going on there. So let's say that we're in some big set S. Here is A. Here is B. Okay, so we'll say that's A, that's B. I don't think we really need the big set, so let me redraw it here. Make these a little larger. So let's just look at a Venn diagram. So if we have A and B, so in here, this would be A union B, right? So A union B complement would be this part and this part, right? So A union B complement would be this and this. So we can see that's the same thing as a complement. I'm sorry. Hang on. That's not the union, that's the intersection in the middle. So it probably, I guess we do need a bigger set that these are all in to really see this. Okay. So A union B complement, A union B would be anything inside of either of the circles, right? So the complement of that would be the outer part. Whatever bigger set that these two are in. And if there isn't one, then it would just be nothing, right? The A complement then would be everything outside of A, including the stuff inside B. But then B complement would be everything outside of B, including the stuff in A. But then when you take the intersection of those two, it would just give you the outer part, right? So that's this one right here. Okay. And now if we look at the other one, so if we have A and B, A and B, the other one states that if you take the complement of the intersection, so basically everything that's not in the middle there, you have A complement union B complement. So everything outside of the middle is going to include everything in the larger set, right? Plus everything in here. Then we have A complement union B complement. A complement would be everything outside of A, including the stuff in B. B complement would be everything outside of B, including the stuff in A. So that's why the stuff in A and B get included here, because it just needs to be in one of them. It doesn't have to be in both of them. Okay. So we'll prove this when we actually look at how to prove set relationships. I think that'll be more informative than really looking at the logical statements, but it's still good to kind of see. So the idea is that when you negate them, the symbol also gets negated, right? Same thing with sets. When you are negating them, which is a complement, the symbol gets flipped, right, from union to intersection or vice versa.